Welcome back to the Deep Dive. Really excited about today's topic. But hang on, before we jump in, please do make sure you subscribe to the YouTube channel Daily Colloquial English. And, share it with your friends.
Yeah.
Sharing knowledge is always good, right?
Okay.
Okay, so let's get into it. Today, we are tackling something massive, literally. The 2025 Nobel Prize in Physics. It's about quantum mechanics, but on a scale that kind of messes with your head in a good way.
It definitely does. The prize itself, the official citation, it's for the discovery of macroscopic quantum mechanical tunneling and energy quantization in an electric circuit.
Right, macroscopic, that's the key word.
Yeah.
And it went to three people, John Clark, Michel Devoret, and John Martinez. Really interesting affiliations there.
Yeah. Clark at Berkeley, Devoret split between Yale and UCSB.
And Martinez, this is fascinating, he now heads up the Google Quantum AI Lab. I mean, that connection alone tells you how important this foundational work really is, even decades later.
Absolutely. So our goal today, our mission, if you like, is to figure out how these quantum effects, the weird stuff usually confined to, single atoms or particles, how they were actually seen, proven in a device with billions and billions of electrons. It's about showing a whole circuit can act like one quantum thing.
Okay, so let's start small then. To get why this is such a big deal, we need to understand the quantum part first, specifically tunneling. So, classical physics. If I throw a ball at a brick wall,
it bounces back every single time. If it doesn't have enough energy to go over the wall, it just can't get through. End of story.
But quantum mechanics says...
Well, quantum mechanics says there's a chance, a probability, that the particle can appear on the other side of that barrier, even if it absolutely does not have the energy to climb over it.
How on earth does that work? Is it like finding a secret door?
Not quite a door. It's all about the wave function. Remember, in quantum mechanics, particles also behave like waves. This wave function basically describes the probability of finding the particle somewhere. So when this wave hits a barrier, it doesn't just stop dead. The Schrödinger equation tells us the wave function decays inside the barrier, gets really, really small, but it doesn't necessarily go to zero immediately.
So a tiny bit leaks through.
Exactly. A tiny part of the wave emerges on the other side. That tiny wave means a small, but definitely non-zero, probability of finding the particle over there. And here's the kicker. Its energy, its wavelength, hasn't changed. It didn't slow down scraping through the wall.
It just appeared, like it teleported.
In a way, yeah. It's as if it tunneled straight through. It's not violating energy conservation, it's just probability playing out in a very strange way.
And this isn't just some weird theoretical thing. You're saying this actually happens.
Oh, absolutely. It's fundamental to how the universe works. Take radioactive decay, for example. Alpha particles, which are like little bundles of protons and neutrons, they're stuck inside the nucleus.
Right. Held by the strong force, but pushed out by electromagnetism.
Correct. That electromagnetic repulsion forms a barrier. The alpha particle doesn't have enough energy to just fly out. But eventually it tunnels through that barrier. The probability of that tunneling event is what determines the half-life of the radioactive element. Sometimes it's incredibly long because the probability is so low.
Wow. Okay, that makes sense. But you mentioned another example. Solar fusion.
Ah, yes. This one's like existentially important for us. Inside the sun, you've got protons, positively charged particles. They repel each other massively. That's the Coulomb barrier.
Like trying to push two strong magnets together, the same poles.
Exactly. And even though the sun is incredibly hot, millions of degrees, the protons aren't actually moving fast enough on average to just slam through that repulsion and fuse.
So how do they fuse to create sunlight?
They tunnel. There's a small probability that when two protons get close enough, one tunnels through the repulsive barrier of the other, allowing the strong nuclear force to take over and bind them. Without quantum tunneling, the sun wouldn't shine. Life wouldn't exist.
Okay, my mind is officially blown. So tunneling is real, it's crucial, but it's usually for what? A few particles. An alpha particle is 4 nucleons. Protons are single particles.
Precisely. We're talking tiny numbers. The Nobel Prize work we're discussing took this phenomenon and showed it works for like 199 billion-dollar particles acting together. That's the macroscopic leap.
9 orders of magnitude difference. That's huge. So how did they get there? What's the bridge from single particles to billions? You mentioned circuits.
Right. To build that bridge, we need another piece of quantum magic. Superconductivity.
Ah, okay. Zero electrical resistance. Stuff we hear about for MRI machines or particle accelerators.
Exactly. At really, really low temperatures, certain materials just let electrical current flow forever with absolutely zero energy loss. They've kept superconducting currents going in labs for decades.
How does that even work? Why does resistance disappear?
It comes down to the BCS theory, named after Bardeen, Cooper, and Schrieffer, who won a Nobel for it. They figured out electrons, which usually hate each other.
The fermions, right?
Yeah.
Antisocial particles.
Correct. They figured out that in these cold materials, electrons can team up. Two electrons interact with the vibrations of the atomic lattice around them, creating a sort of temporary positive distortion that pulls them together. They form a Cooper pair.
So two electrons pair up, and then what?
Then they start acting like a completely different type of particle, a boson. And bosons are social. They love being in the same quantum state.
Okay.
So all these Cooper pairs, millions, billions of them, can all collapse into the exact same lowest energy quantum state. They form this giant, coherent quantum wave flowing through the material, a Bose-Einstein condensate, essentially.
Like a single massive quantum object made of electron pairs.
You got it. And because they're all moving as one single quantum state, there's no individual electron bumping into the lattice and losing energy, hence zero resistance.
Right, okay. Superconductivity means Cooper pairs acting as one. So where does tunneling come back in?
Well, another Nobel laureate, Josephson, predicted back in the 60s that these Cooper pairs could do something amazing. If you put a really thin insulating layer, just a few atoms thick, between two superconductors.
That's the Josephson junction.
That's the Josephson junction. He predicted that the entire Cooper pair, as one unit, could quantum tunnel across that insulating barrier. And he was right. Won the Nobel in '73 for it.
Okay, so Josephson showed a pair can tunnel, but Clark, Devoret, and Martinez were asking something much bigger.
Much bigger. The theoretical physicist Anthony Leggett had asked the question around 1978, can we go beyond just pairs tunneling? Can an entire electrical circuit built around one of these junctions behave like a single quantum object, like an artificial atom?
An artificial atom made out of wires and junctions? That's a wild idea. How would you even test that? What part of the circuit acts like the position of this atom?
Good question. They used what's called a current-biased Josephson junction. In this setup, the state or position of the circuit isn't a physical location, but a mathematical property called the phase difference between the quantum wave functions of the superconductors on either side of the junction.
Okay, phase difference, like how much the two waves are out of sync.
Exactly. And this phase difference creates a potential energy landscape for the circuit. You can picture it like a hilly terrain, or maybe a roller coaster track with dips and wells.
So if the circuit was just classical, like a normal circuit,
then the phase difference could settle anywhere in one of those wells. The roller coaster cart could stop smoothly at any point along the bottom of a dip. Continuous energy states.
But if Leggett was right, and the whole circuit is quantum?
Then it shouldn't be continuous. It should be like an atom. It should only be allowed to exist at specific, discrete, quantized energy levels within that potential well. Like the roller coaster can only stop on specific, fixed steps on the track, not in between.
That was the big question they had to answer experimentally.
That was the multi-million-dollar question, yes. And the challenge, as you said earlier, was immense. They did this work at UC Berkeley in the 1980s, and it took years.
I bet. You need it incredibly cold, right?
Oh, yes. Near absolute zero. We're talking fractions of a degree above 0 Kelvin. The whole thing had to be in a cryostat, shielded meticulously from any external electrical noise, magnetic fields, even vibrations. Any tiny disturbance could destroy the delicate quantum state.
And they wanted closed logic, you mentioned. What did that mean for the experiment?
It meant they wanted to predict the outcome using only things they measured independently beforehand. They measured the circuit's resistance and capacitance very precisely. Then they plugged those numbers into the quantum mechanical equations.
No fudging the numbers after the fact.
Exactly. They wanted the theory, using their pre-measured values, to predict exactly what they should see experimentally. No fitting parameters allowed to make the curves match. If the results lined up, it was real.
Okay, so what was the first big piece of evidence they found? The tunneling part.
Yes, the macroscopic tunneling. They basically put the circuit into one of those potential energy wells by applying a specific current. Classically, it should just stay trapped there. But they slowly ramped up the current, effectively tilting the potential well. Quantum mechanics predicted that at a certain point, the entire system, All billion Cooper pairs, represented by that phase difference, should tunnel out of the well all at once.
And did it?
It did. They saw a sudden jump in the voltage across the junction, exactly when the theory predicted the tunneling escape should happen. They measured this escape rate many, many times, and the point where it occurred consistently matched the prediction based on their measured R and C values.
So proof that a billion Cooper pairs tunneled in unison. Macroscopic quantum tunneling confirmed.
Confirmed. That was huge. But it wasn't the full story. They still needed to prove the artificial atom part, the quantized energy levels.
Right, the discrete steps on the roller coaster track. How did they show that? You mentioned a microwave antenna in the setup.
Yes, that was key for the second big finding, energy quantization. Think about how we know real atoms have discrete energy levels. They only absorb light, photons, at very specific frequencies, corresponding to the energy difference between those levels.
Like spectral lines.
Exactly like spectral lines. So they treated their circuit like an atom. They used the microwave antenna to send microwave photons into the circuit.
And they basically tuned the frequency of the microwaves.
Precisely. They swept the microwave frequency. If the circuit's energy levels were continuous, classical, it should have absorbed energy smoothly across a range of frequencies.
But if it was quantum, with discrete levels,
it should only absorb energy when the microwave frequency exactly matched the energy gap between two of its allowed quantum levels. And that's exactly what they saw. Sharp peaks in absorption at specific frequencies.
like tuning a radio. You only get the station at specific spots on the dial.
Perfect analogy. They found the discrete energy levels. They even saw that tunneling happened faster from the higher energy levels, just as quantum mechanics predicts. That was the definitive proof, the nail in the coffin.
An entire electrical circuit behaving quantally with discrete energy levels, just like a giant engineered atom.
That's the achievement. Billions of particles acting as one coherent quantum object with measurable quantum properties like tunneling and discrete energy states. That's why this work, done 40 years ago, warranted the Nobel now. It fundamentally changed things.
So what did it change? What's the legacy today? We talked about Google quantum AI.
Well, this work basically kickstarted the entire field of superconducting quantum computing, those circuits they built. Miniaturized versions of them are now used as quantum qubits.
The building blocks of quantum computers.
The very same. When you see those pictures of quantum computers, the big fancy chandeliers.
Yeah, it looks like something from science fiction. All those nested golden cans and wires.
Right. Most of that intricate structure, maybe half the mass, is actually just the dilution refrigerator needed to get things down to millikelvin temperatures, even colder than Clark, Devoret, and Martinez needed.
Colder than outer space.
Much colder. But down on the chip, at the very bottom of that chandelier, the actual qubits, they are often tiny superconducting circuits, crucially involving Josephson junctions, designed to act as these controllable two-level artificial atoms.
Based directly on the principles they proved.
Directly. The ability to control the quantum state of the circuit, to put it in superposition, to entangle it with others, it all relies on that circuit behaving as a coherent quantum entity. Martinez going to Google is just the most visible sign of that direct lineage from fundamental physics experiment to cutting-edge technology. His team's quantum supremacy paper a few years back used exactly this kind of superconducting qubit technology.
Incredible. So, for you listening, the big takeaway here is this wasn't just about proving some obscure quantum effect. This Nobel Prize celebrates the moment we learn how to take quantum mechanics, usually hidden in the subatomic realm, and engineer it onto a chip.
We learned to build and control artificial atoms. That capability is the foundation for much of the quantum technology revolution we're seeing start to unfold. A huge win, especially for the 2025 year of quantum physics.
Definitely. But, it also brings up a deeper question, doesn't it?
It does. Philosophically, it's quite profound. We've shown quantum mechanics isn't just for the very small. It works for systems of billions of particles, things we can make and see.
So does making the quantum system bigger help us understand that weird transition between the quantum world and our everyday classical world, the infamous measurement problem?
That's the million-dollar question, maybe the trillion-dollar one.
Yeah.
Does demonstrating quantum effects in a macroscopic circuit bring us closer to understanding why measuring a quantum system forces it into one specific state? Or does it just mean the mystery itself scales up?
We see the quantum weirdness survive on a larger scale, but maybe the dividing line just gets pushed further out.
Perhaps. It shows the quantum rules apply more broadly than maybe some expected, but whether it resolves the fundamental nature of measurement, that's still very much an open debate.
A fascinating thought to leave people with. We've seen how quantum tunneling works, how superconductivity enables macroscopic quantum states, and how an entire circuit was proven to act like an artificial atom, paving the way for quantum computers. But the ultimate question of why the quantum world looks so different from ours when we look closely, that remains.
Plenty left to explore there, or maybe delve into the quest for room temperature superconductors next time.
Absolutely. Thanks for joining us on this deep dive. We'll see you next time.